How's it going?
Good.
Good. All right. Um, yeah. Why don't we get started 1 minute early? So last time we started a second way of dealing with the problem of interchanging a derivative with a infinite time average, right? So this is really important when we want to look at error analysis. For example, the impact of numerical errors or mesh to a statistics of a ergodic system, or we want to perform optimization, which requires us to compute the derivative of certain statistical objective function with respect to a design parameter, right? So we studied two methods. One method is using a windowing method to basically reduce how much oscillation there are in the objective function. So going back to our earlier notebook, so we defined the van der Pol oscillator a periodic orbit, and when we solve it, we find out that the linear solution, so this is the plot of the linear solution, just grows linearly when we perturb a parameter, right? And we are able to visualize the linear solution. It turns out to be the growing part turns out to be tangential to the trajectory, and so this is, I think, the linearly growing tangent solutions. So we are also able to plot what the solution what the solution as a function of a parameter looks like, right? So we made the parameter mu to be a series of different numbers, and I change it. So instead of going from 0 to 1, we can actually visualize the plot a lot better if we let if we get rid of the mu equal to 0 location, because when mu is equal to 0, the system is actually not really a limit cycle, right? So if you look at the definition of the system, when mu is equal to 0, so basically we have the simple linear harmonic oscillator, which actually could be oscillating around at any magnitude, right? So if we have mu equal to 0, so basically to avoid essentially a singularity problem in the parameter dependence, I changed the notebook so that we would be looking at a region. Instead of from 0 to 1, we are looking from 0.2 to 1.2. All right. So after that change, we are able to visualize how the long time average of, which we denote as J bar, right, which is really a long time average of the square of the x, or the mean magnitude, or the L2 norm in some sense of the x, would depend on the parameter. So here we looked at two different lengths when we averaging over the first half of the period. So J bar 1 is actually the average over the first 100,000 time steps, which corresponds to, since we have a delta t of 0.1, right, it corresponds to first 1,000 time units. We get the blue plot. And if we average over the whole trajectory, which has 2,000 time units, we get the orange trajectory, right? As we can see, the orange trajectory has much smaller oscillations. Well, not much smaller, it has half as much oscillations, but the frequency of the oscillation actually also doubles. As a result, if you compute the derivative of that objective function, right, you would not get a derivative that approximates the overall trend of this objective function. All right, so that's basically by changing the parameter range and exclude the 0, we see the oscillatory behavior a lot better. Okay, so just as a mental exercise, what do you think if you perform an infinitely long time average, right, and get rid of all the small scale oscillations? Can you just look at the plot and estimate what is the derivative of this objective function with respect to the parameter, right, just by examining the plot? It's kind of linear, but what is the derivative? the slope, yeah, can estimate it numerically just by, for example, watching what the plot is like. It's about 0.1, right? So if you look at the range from 0.8 to 1.2, right, the x-axis or the parameter mu rises by 0.4, and if you look at the y-axis from here to here, it rises about so the gap here and the gap here is similar, right? So from here to here is also 0.04, right? So if you divide the delta y by delta x, the derivative is roughly 0.1. All right, so well, that's something you should be looking for your homework, right? But let's see how we are able to today compute this derivative using the time dilation method. All right. Well, this is really another illustration of basically when we plot the solution at the end of the first time period and at the end of the second time period, we see that the phase actually decorrelates a lot more when we look at the end of the second longer time period. Okay. What did we? Yeah. So this is let's get to the end, because here we were looking at the simple system, right? Simple system illustrating the windowing effect, and this is what we did at the end of the last lecture. That is, after we project the solution out of the time evolution, we'll project the tangent solution out of the time evolution direction, right? We get a non-growing tangent equation. A tangent solution instead of a growing tangent solution. Okay, just to review the time dilation method. So we started with the assumption that we can decompose the effect of a parameter change, and as the result, a delta f, into two parts, right? Delta f1 and delta f2. And the linearity assumption, right, assumes that the time averaged objective function is a linear function locally of a small change in f. Okay, so that is basically assuming that the statistics is differentiable with respect to the right-hand side of the differential equation. Okay, so in a functional analysis sense, a functional being differentiable means the map from a small change of the function to a small change in the objective function is linear. Okay, and in fact it's linear, and the linear operator is bounded. So we're not going to go into the boundedness of a linear operator today, but like this is basically the linearity is a key issue underlying the differentiability of the objective function. Okay, and with that linearity assumption, we decompose the delta f into two parts, and we should see that the resulting change in the objective function should be just the addition of the result from these two delta f's. And what are these two delta f's? The two delta f's are such that the first delta f would only change the location of the limit cycle, but not the attractor, right? And the second delta f does not change the location of the attractor, but only changes the period. Okay, and we have shown that we can solve these two parts by projecting a solution, a regular solution of the linearized equation, which actually grows in time, into the direction orthogonal to the time evolution direction. So that would correspond to the solution of the tangent equation with the first delta f, with a delta f1, right? So that's the first equation. Okay, and we don't even have to solve the second equation, because we have derived that the chi, which is the time dilation term, right? So the second delta f2, is actually equal to the chi times the direction of time evolution, the right-hand side of f, right? So basically the second delta f is chi times f itself, which really corresponds to an acceleration or deceleration of the evolution. Okay, and the chi we derived, it's simply the time derivative of what is projected out from the original tangent solution. So today let's actually follow this logic and try to implement it in our numerical Python notebook and see what we can get, right? So first of all, before I start with the numerical implementation, do you have any questions, additional questions on this approach? Okay, so if no, let's actually start by computing the first part of the delta J. The delta J due to the delta F1, which does not change the period. Okay, all right. So how do we do that? Here, we already obtained the V, right? That is the solution. So let me actually call it V1 is equal to V minus that, right? So basically that is our the solution to our first tangent equation corresponding to delta F1. And whenever I have V, let me just change it to V1. Okay, let's run this and make sure it works. So on the left-hand side, it visualizes what V1 is, and it is actually orthogonal to the trajectory. On the right-hand side, we are plotting V1 as a function of time, and we see, except for the first part of the trajectory where the nonlinear system has not reached the limit cycle yet, right? So it's the first part of the system. The system is purely periodic. It has no linear growth in time. Well, that is a little bit, that is not strictly true, because if you look very carefully, I don't know if that's obvious or not, there is actually a slight growth in the magnitude, right? And we're going to discuss why there is still a very subtle growth in the magnitude. And this is actually because of the numerical time integration, right? So we have derived all of our time dilation method based on the assumption we are solving the ordinary differential equation exactly, right? We have derived that the ddt is a solution to the tangent equation based on an exact solution of the differential equation. And therefore, when we project out, we project exactly on the du dt direction. But when we solve it numerically, it turns out that f is almost what we need to project out, but it's not going to be exactly what we need to project out. We'll study later, like how that affects things when we that actually affects things when we change the length of the trajectory to be much longer than what we are doing here, right? But let's just ignore the fact that there is a tiny growth on the projected solution for now. Okay, so how do we compute? Any questions on that? If no, let's figure out how do we actually compute the delta J bar caused by this particular tangent solution, right? So we have analyzed by the end of the last lecture. We have noted that the delta J1 can simply be approximated by this, right? When t is very large, delta J1 can be approximated by a time average of the partial derivative of the instantaneous objective function to u, right, times our tangent solution. So in this case, what is our dj du? Right, remember, like, our j is what? Our j in the case we were looking at is u0 squared, right? So dj du should be just u2 times u0 So let me see, what is my solution U? My solution U is actually the real part of my U0, right? Okay, so dot real and zeros like did I U0 dot real. So that is the derivative of my objective function with respect to the let me just make it U1 so that it is clearer, right? So because the objective function only depends on U0, it doesn't depend on U1, so the second part is corresponding to U1 is 0. The first part is 2 times U0, right? Okay, so the product, this is dj du. The product of dj du with v should be dj du times v1. So remember, v1 is the solution projected out, right? So that corresponds to the first tangent solution corresponding to delta f1. So that dot sum 0, right? That is the dot product should be what is inside of this integral. Okay, so let's just plot it, solution dot t with this dot sum dot 0, and make sure that it is actually something that's stationary, right? So this is actually this thing needs to be averaged in order to obtain this approximation to delta J1. All right, so in particular, what I usually like to do is cum sum of these. So if this actually lies on a linear slope, then that linear slope is the time average we are looking for, because we are always needs to be ignoring the first part where the trajectory itself has not reached the linear cycle yet. And again, we see that there is a slope, but the slope is not exactly linear, right? So it hasn't reached like seems to be a steady state yet. Let's actually increase the length of the time integration by a little bit. Let's actually make n steps. In this case, 10,000, and dt equal to 0.01. And the length of the time is n steps times dt, and let's see, this is n steps times dt, and n steps plus 1. Right, so now let's actually make the number of time steps a little bit longer to make sure we still make sure we get a good solution. So now this has gone for a little bit longer, and let's plot this out. Okay, so now we have now seen like this is reached a very linear line, right? So the slope of that is really the time average we are looking for. Okay, so what is that time average? Let's actually compute it by the following. So let's print out the average of that. But instead of just averaging that, let's actually skip the first part where the slope is not exactly linear yet. So let's skip the first 100 time units, right? Which for the time steps is skipping the first 10,000 time steps. So let's look at what the slope is. Well, because we remember, like, we perturb the parameter by 10 to the minus 100, right? So when we solve the tangent equation, the argument, let's actually make it here so that we can see it. The argument mu has been perturbed by 10 to the minus 100. So when we look at the derivative, right, we should also divide it by 10 to the minus 100. So the derivative, sorry, right. the derivative turns out to be minus 0.26. All right, so that is actually very different, right, from what we estimated previously on the slope of the plot. We estimated that the slope of the plot we just saw was more like 0.1, right? It's positive and has a lower magnitude. So why is that? So what are we missing here? Smaller time step? Not actually, because we are only computing part of the sensitivity, right? So previously on the plot we have shown up here, we are changing the parameter mu and looking at, as a result of the change in the parameter mu, the right-hand side of the ODE has changed, and we are looking at the result of the delta F caused by a change in delta mu. But in the time dilation approach, we have split the delta F into two parts. One part changes only the trajectory, but not changes the location of the limit cycle on the phase space, but not the period, right? The other part changes the periods. So these derivative or this perturbation only accounts for the first part, right? It did not account for the change in the period, or it does not account for how the density on the location of the trajectory has shifted as a result of the parameter change. Okay, so that means we need to look at another component. All right. One is that. Okay, so what is the second component? So let's look at our discussion on Monday. So Monday, we derived the effect of the time dilation term by going back and forth between the time domain and the phase space, right? So we first derived that the density, or the equilibrium density, right, which is really represented by the percentage of time an infinitely long trajectory spanned within a particular segment of the limit cycle, is actually equal to delta t over the period, where delta t is the amount of time it takes for trajectory to go through that segment, which is delta s divided by the speed, right, of the evolution itself. And then we represented the J bar, the time average, instead of as a time average, as a spatial average weighted by this stationary density. Okay, and then we used that formula to figure out the effect of a small change on the speed of the trajectory, which is really delta u du dt, which is f itself, right? So basically, when the speed is accelerated by a small percentage represented by this time dilation c, we have derived through a set of a small perturbation Taylor series analysis that the resulting delta j due to the acceleration or deceleration is really an infinite time correlation between the difference between the local objective function and the global time average objective function and this local acceleration, right? So this result makes sense in that if c is positive, that means I'm skipping this segment faster, Therefore, the resulting effect on the objective function is negatively correlated with whether the objective function locally is greater than average or less than average. Okay, if I'm slowing down, which corresponds into a negative c, the trajectory lingers at this location for longer. Therefore, its result to the time average of an objective function is positively correlated, right, with if the local objective function is greater than the long time average. Okay, so basically what we need to do is really just to compute the correlation between the local objective function and the time dilation. Right. By saying correlation, I literally mean correlation because it actually, we can further make a derivation here, right? That basically saying that happens. Okay, basically saying that this quantity actually doesn't matter if you add another term. T. If instead of writing chi, you can write chi at this particular location of the trajectory minus chi bar, right? The long time average of chi dt. It doesn't matter because the contribution to this term, right? This term is constant. It doesn't depend on t, right? So if you look at the effect of this term only, you can move this term out of the integral, and the j minus so the long time average of j minus j bar. Oh, so there is no bar here. This is just a j. The long time average of j minus j bar, of course, is 0, right? So it doesn't matter if I subtract a chi bar over here. So this is literally the correlation, right? The product of the difference between the instantaneous j and its minus its average, instantaneous chi minus its average. Actually, it's the negative of the correlation because I need to, yeah, for the in the definition of correlation, it's j minus j bar and psi minus chi bar. So this is really the negative of the correlation. Okay. Yes.
I may have missed this, but is chi user defined, or is there like a theory for calculating?
Oh, there is it's determined by the derivative of the how much we are projecting out.
Okay.
Yeah, so chi is basically what needs to be subtracted from the first equation, from the first tangent equation, such that the solution of the tangent equation would always be orthogonal to the f, to the du dt. Right, so it is the term. It is basically the delta f2 that needs to be subtracted from delta f, such that delta f minus delta f2 is actually the delta f1 we are looking for. That does not change the period. All right. Okay. So yes. So the first task is actually for us to compute the chi. All right. So we already have, by projecting out, we already have this a quantity that needs to be projected out. So let me just call it projection is equal to this guy. And so that when we project it out, we just say v minus projection times f. Okay, so let's actually visualize what that projection looks like first. Right, is recalculating that, and now let's actually start to compute the second part by first plotting solution.t and this projection. Okay, we see that second. Okay, so this projection actually, wait a second. There should be a linear growth term somehow, but this actually doesn't really come up. Let me see what happens over here. Okay, so let me just make sure I don't have a bug in the code by actually printing out what the original solution V is like. Okay, so I'm plotting. I have 4 plots now, and I want to plot not just the V1 but also 0, 0. I want to plot not just the V1 but also the original V. Sorry, okay, X is 0, 0. And I do remember I see a linear growth in V, but here I don't see a linear growth in V. One second. So let me just double check I'm solving things correctly. Go to 1. Let me just method equal to rk3 to 3, just to make sure I'm solving things right. Oh, okay. Yeah, I think I think that the default integration method actually somehow messes things up. Basically, the default integration method, I think when it deals with a small imaginary component, it actually had some issues. I haven't figured out exactly what it is yet, but like if I specify a typical time integration method, it actually fixes the problem. Okay, so I do see this very rapid linear growth in the non-projected solution, and this is the projected solution. We do see actually a small linear growth over here, but we're gonna see we'll fix it later by actually, instead of projecting out the exact time evolution direction, we'll actually project out something else, project out a solution to the homogeneous tangent equation, which should actually be du dt if we are integrating things exactly. And we can also reduce this by specifying a lower tolerance, right? So okay, options pi psi pi solve IVP. So if we can specify a lower tolerance on the solution, right, so ATO and for example, if we specify something smaller than the default, let's see what is the default for that. Right, default is 10 to the minus 3. So if we specify a tighter tolerance, right, we should see that the projected linear solution actually stays with a fixed magnitude for much longer. So basically, it shows that the original linear growth we have seen on the projected tangent solution is actually due to the time integration being not precise, right? Okay, and then let's actually recompute this, and yeah, so again, like basically, instead of plus 0.1, we see that the first part of the delta F gives us a sensitivity that's negative 0.08, right? Almost the opposite of what we expect. Okay, so now if we look at yeah, so the part we are projecting out, we see that it grows in the negative direction, right? So what does that mean? That means our xi, which is the time derivative of this projected out quantity, is negative, right? And what does a negative xi mean? What does a negative, on average, negative xi mean? Orbits are slowed out, exactly. So that means a larger parameter mu would correspond to a longer period, right? Okay, and if we can zoom in a little bit more, so let's say, actually let's make multiple. Let's make multiple figures, and let's zoom out a little bit. So focus in between 0 and 10, for example. We see that, well, we also actually, let's actually make another plot. Let's make another plot, just the first part of this project out solution. We see that it actually doesn't just go down monotonously as this plot might suggest, right? So it actually goes up and down, up and down, up and down. So the derivative actually is not just a constant negative value. It actually is positive for a lot part of the trajectory and negative just for a bit more part of the trajectory, right? So essentially the increase in the parameter mu doesn't just decelerate the solution everywhere, but it just accelerates the solution. Actually, here is an acceleration, right? It accelerates the solution in some parts, but decelerates in a larger part of the loop. Okay, so this is really important in computing that part of the sensitivity accurately. So let's actually compute the xi. Right, xi would be equal to, let's do a central difference. So projection of central difference would be, oh, okay, so let's actually stack them up. The first one, let's just take a finite difference in one-sided way, divided by dt. Right, so I think I have a dt parameter set previously. Yes, I do. Okay, and then the middle part is projection from 2 to projection minus 2 to minus 2 divided by 2 times dt, right? So, and then projection of minus 1 minus projection of minus 2 divided by dt. Okay, so that basically would give me a xi that's as long as my my t, right? Okay, and let's visualize what this xi looks like. It's actually also plotted on both sides. Oh, sorry, I mean on the lower plots. So yeah, so basically we see a xi that's also pretty much periodic, right? So that's good news, because that's what we want to compute the long time correlation between this xi and something, and the objective function locally. And the right hand side shows that the xi is actually on average negative, but like it goes up and down throughout the trajectory. And finally, let's actually compute the correlation, right? So print, how do we compute the correlation? It's the mean of, actually, let's just compute j mean is equal to, so u0, right, dot real dot mean, okay, and compute xi mean being xi dot mean, okay, and then the correlation, which would give us the sensitivity with actually the negative of the correlation, or let's just say j mean minus u0 dot real times xi minus xi mean. Actually, the second part doesn't matter. You don't have to subtract with xi mean. You get the pretty much the same result unless you use some windowing here. This dot mean. Let's see what we get. We get this 10 to the minus 104. I think there might be a is there a delta t that I'm not taking into consideration here? Oh, sorry. J is not just a u0 dot mean. It's u0 square dot mean, and yeah. So this is actually squared, right? So because we are looking at an objective function that's square of x. All right, so we get this quantity, and again, we need to, this is the effect of perturbation in the parameter with the magnitude 10 to the minus 100. So divide by 10 to the minus 100, we get 0.19. Okay, now it's time to combine these two delta j's, right? So the second part, the time dilation, gives us 0.19. The first part gives us minus 0.085. So let's just combine them. Actually, it might be good to also just get rid of the first part of the trajectory because it has not stabilized yet. Okay, so that's just removing the first part of the trajectory, and also xi, I'm removing the first part of the trajectory. So in the correlation, I also want to remove the first part. Okay, and then let's say let's actually just give them a number, right? So dj1 is equal to this. Okay, and my dj2 is equal to that. And finally, let's print dj2 and also print dj1 plus dj2. So the final number we got is about 0.11, right? So that's if you do a very careful study by averaging over a really long time to smooth out all the oscillations, and compute multiple values of mu over here, right? And basically do a linear regression, you can also get the same quantity, right? Alternatively, for periodic systems, you can exactly like what you are assigned to do in the homework, right? Compute the period and average over a period, and do the same thing to get the value. So just curious, how many of you did the homework and got the same number? Got something different? Okay. Okay. What oscillates? Okay. Okay. I mean, first thing to check is do something similar to what I did here to make sure the numerical time integration error wouldn't affect your solution by that much, right? So changing the tolerance would always, I mean, so you want to change the tolerance to low enough that this further making small doesn't really affect your answer, right? But that means your your time integration has been good enough. Okay. Any questions so far?
Just to make sure, the derivative we calculated was at fixed mu, right?
Yes, it's the derivatives we are trying to calculate is the derivative around a mu equal to 1, right? So because in solving the tangent equation, that's what we specified. Mu is equal to 1.0 plus a tiny perturbation and on the imaginary direction, so that we wouldn't round of error wouldn't overwhelm it, right? Any other questions? Okay. Finally, I want to touch something that it's very subtle, and nobody really understands how to rigorously deal with yet. So that's what happens to this time dilation approach when we cannot afford to integrate the solution to however small tolerance we want. That is typically the case when you look at a large system, right? So when you solve a PDE rather than an ODE, if you want to solve a very complicated system that by itself takes a lot of time to calculate, it's not always feasible, really, to just set the tolerance of the time integration to small enough that further changing it to smaller wouldn't affect the answer, right? And this has actually a pretty significant effect on the sensitivity analysis, as we have just seen when we actually had the tolerance of 10 to the minus 3, which was the default. So let me actually copy this part and paste it down while not setting the tolerance to so high, just setting it to 10 to minus 3, right? So what we should see here is that everything else looks right, except for the tangent solution. Even after projected out, it's still growing, although it grows much slower than before you project it out, right? But it's still growing. So let's see how does that affect the downstream computation. So if we also copy this part, which actually computes the first part of the derivative, we see that actually it affects it by a lot, right? So instead of a minus 0.08, we actually compute a much smaller number. And the reason we are computing a much smaller number is because due to this growth, we are having actually instead of having like a constant slope, when we are adding up the so let me go back to this, right? Oh, so that's the delta J part, right? So what we are showing is the integral from 0 to a variable t, this quantity, right? So instead of this quantity increasing linearly, and therefore by dividing it by a big T, we are getting a well-defined average, we are seeing something different. We are seeing this integration actually goes up, right? So the slope actually changes, and if you solve it for longer, the slope is going to keep changing. Okay, so we don't really have a well-defined average. So how do we deal with that? Well, one way to deal with that is actually not assuming that f is the direction you want to project out, but rather we want to actually solve numerically the homogeneous linearized equation. So what does that mean? That means I'm going to be solving not just a inhomogeneous tangent equation, I'm also going to be solving a homogeneous tangent equation. So let me just copy this thing from here, and I'm going to show what I mean. So here is what I'll be doing. So I'm going to be solving two equations instead of a single equation. Okay, and instead of let me say, instead of a ravel, I'm going to make it an array, and instead of adding a zero imaginary component, I'm going to be adding I'm going to be use zero. I'm going to be adding a 10 to the minus 100 j on the first equation. Actually, this is no, on the first equation. That's what I mean. Right. So basically, I'm perturbing the initial condition for the first solution by a little bit. All right. Okay. And then instead of perturbing the parameter, which is mu here, uniformly by 10 to the minus 100 j, we are going to be setting a parameter that is not perturbed for the first equation, but perturbed only for the second equation. So the argument is going to be mu. And u0 is going to be array, no, ravel u0, so that the solver is able to accept the initial condition. Okay, is it clear what I did here? So I'm solving two equations, the same equation, except for the first equation does not have a perturbation in the parameter, but instead it has a perturbation in the initial condition. And the second equation has a perturbation in the parameter, but does not have a perturbation in the initial condition. Okay, so I'm solving a homogeneous tangent equation and an inhomogeneous tangent equation. We have previously visualized a homogeneous tangent equation and shown that the solution pretty much aligns with the time evolution direction. By pretty much, I mean exactly, only if we solved the ODE exactly. If we haven't solved the ODE exactly like what we're doing here, then there is going to be a tiny misalignment, right? And we're going to see that tiny misalignment actually matters. All right. So we solved the solution, and now we have to have two solutions, right? And so actually, let's actually just take it dot. So that's the real part of the solution, and we, because the two solutions should have the same real part, we just take any one of them. And now I'm going to have two v's. Solution dot y the reshape 2n minus 1. So this is the homogeneous solution, and this is the inhomogeneous solution, right? Okay. And now I have my f, but instead of projecting out, let me say v1 corresponds to the previous solution, right? So let me say projection with f is equal to this, and v1f is equal to v1 minus this times f. But let's compute another projection. Let's project out, instead of f, we project out the tangent, the homogeneous tangent solution. So v1 times v0 divided by v0 squared. Okay, and v1 projected by v0 is equal to this times I think the, oh sorry, I shouldn't be changing this. I should be changing this v0. Okay, so I have two versions, and in the continuous limit, in the limit of exact time integration, they should be exactly the same, right? But in reality, we are going to show that it is not going to be exactly the same. So the first two plots should be the same, and now down here, I'm going to be plotting two of these. One is projected out by f. The right-hand side one is going to be the one projected out by v0. So let's see. Where are we? The visualization is kind of messed up because I should actually be visualizing the projected out version. Let's visualize the projected out version by v0. Okay. Oh, there isn't v dot t. There should be v1 dot t, right? So, but it's the same. Why is the visualization still 10 to the 101? Yeah, is there... Yeah, at some point I'm dividing by 10 to the minus 100 twice somewhere, so that I got such a big value. So v1 is still right. Okay, so I think I probably have a problem with the projected. So v0 is the solution to the homogeneous equation. That seems to be right. Okay. Yeah, I think I have a problem with the... Oh, yeah, that's... So v1 times v0 divided by v0 squared. Oh, it's not multiplied by f, should be multiplied by v0. Yeah, sorry. So this is the projection. Okay, so let's run it again and see what we get. Okay. Something is wrong here. It's 18. So I'm not getting the... I'm not even getting the same value as I got before on the v1f. Oh, okay. So my f is du dt u dot real. Yeah, that's no problem. it looks like the projection didn't really do anything, right? Or it did something, but it's wrong. You see, my U0 is okay. F is still the right F. Okay, so actually, let me instead of plotting this, let me actually plot V0 just to see what V0 it looks like. V0 should be a solution that's okay. So this is V0, right? So V0 is a solution that's, so as we see, instead of being F, which is, so if we look at the right hand side, F should always have the same magnitude no matter which period we are, right? So, but because of the non-exact time integration, we see that the solution to the homogeneous tangent equation actually has a slight decay over time. So instead of being perfectly periodic. But what's happening here? Shouldn't affect this. Let me just comment this out, and I think we should get the same. One second. So let me just go back to our original. Yeah, if we go back to our previous plot, yeah, so we get this mildly growing solution. So basically, we the first task is trying to reproduce that, right, with our two tangent solutions. So let me just make n equal to 2, n dot real, and solution dot y dot image, and let's make sure we get the same thing. One second. 4. Oh, okay. We have to reshape it. has to be okay. U has to be just the first. We have to just take one of the two solutions from U. Okay, so basically we're solving two equations right now, and both equations are the same equation, right? But then it's already not the same as before. What's wrong with solving two equations? So if we just solve one equation, we should get, okay, take the first solution. Just to solve one equation, we should get the right thing. Yeah, if we solve one equation, we get the right thing. We solve two equations, somehow it's different. Okay, we actually get the same thing if we take the first solution. And we would not get the same thing if we take the second solution for some reason. Let's see. V1F is equal to V1 projected out 1, and so let's actually see what happens if we project. Yeah, so if anybody sees where the bug is, let me know, because somehow when I'm solving two equations simultaneously, I get while feeding in this equation. Oh, I think I understand what is happening. So I'm actually feeding a random initial condition. So into these two equations. So these two equations actually have two different initial conditions, and therefore their phase is going to be different, right? Phase is different means when I'm projecting out the f, I'm projecting out different f's. So if I make them the same initial condition, I think it should fix the problem. It's basically I need to make sure they have the same nonlinear solution. Yeah, okay, then it works. Now let's get back to our original plan. So we make an array, and we're going to be perturbing the initial condition, but only for the first equation, right? And our mu should be perturbed only for the second equation. So my argument should be mu and that, and I'm going to be ravel u0. Okay, and so here's my u, the v0 and the v1. Okay, so let's say I'm projecting out with the f should be v1 times f by this, right? And my v projected out with f should be v1 minus projection out at f, and then my projection with v0 should be this times replacing f by v0, right, by the homogeneous solution. Should be v1 minus v0 times v0. Okay, so when I'm visualizing, instead of v1, I want to visualize with the projection, right? v0 okay, and then I'm plotting my v1.t, which is the before the projection, and then I want to visualize v projected out with f and projected out with v0. So let's see. This time it gives us the right thing. Okay, yeah. So this time we have shown that on this plot, right, we have shown what we have seen previously when we project out the f component. We have seen a slight growth. And on the right-hand side, we are projecting out the solution corresponding to our homogeneous tangent equation, which in the continuous limit actually should give us something proportional to f, right? And then let's also print our solution.t, right? So this is the projection with f. Let's actually plot our previous solution on the left-hand side and the better projection on the right-hand side. And if we project it out f, we should get this. If we project it out v0, we should get this, right? So let's print this both parts. All right, so on the left-hand side, we see that the slope was changing, right, due to the inaccurate projection. And on the right-hand side, we get the linear slope. And if you look at the numbers, right, if we project out just the dU/dt direction, we get the wrong number on the right-hand side. Even with much less tolerance, we get a number that's pretty much the same as what we have got before, which is here, right? Okay, so this is just the one thing that we have to be careful when we are dealing with time integration, with time dilation, when we are integrating the differential equation not exactly. And it turns out there is an analogous problem with the second part, with the with actually computing the correlation, except for often the second part is a little bit more tolerant to time integration errors, but still it's something that essentially it's still a research topic on how to deal with non-exact time integration in this framework. All right, so if you are interested in looking more into this aspect and figure out something better, that's going to be a good research paper. All right. Okay, any questions on this? All right. Okay. If no, this is really the end of the periodic limit cycle discussion, right? So basically what we have learned is that we are essentially using the periodic limit cycle as a simple playground to discuss a lot of the problems and algorithms that are useful in chaotic systems, right? So we have looked at the Poincare sections, right, which are essentially like for two-dimensional periodic systems, the Poincare sections are essentially one-dimensional maps, right? And how do we understand the periodic system from that point of view? We looked at the concept of ergodicity, right, which allows us to translate back and forth between time average and a phase space average with the ergodic probability measure. We have also looked at the Lyapunov exponents and have seen that for periodic systems, we get a bunch of negative Lyapunov exponents, but also a one that's exactly equal to 0, at least for continuous time systems. And then finally, we looked at the effect of the 0 Lyapunov exponent in the tangent solution and in sensitivity analysis, and have shown that even a 0 Lyapunov exponent introduces significant problems that we have to deal with, either using a windowing method or using a time dilation method. So all of this is going to be useful for chaotic systems, and which is really what we are going to start. Don't have much time today, but we are really going to start next week. Somehow. Running out of battery. Okay. No. Anyway, I think I can last for 5 minutes. So what are the what are we going to look at to start with for chaotic systems? We're going to start with what I personally define as simple chaos. So what does simple chaos mean? Simple chaos means the kind of systems that are not really spatially extended, right? So something that's different. On the opposite side of a simple chaos, it's really spatially extended chaos, something like turbulence. Okay, so the simple chaos are systems like what we are seeing here. So this is a typical example of a chaotic but not really turbulent flow. So this flow is actually modeled with what's known as unsteady Reynolds averaged Navier-Stokes. So it actually models all the supposed turbulent flows. But even for this case, there is this very strong vortex coming out of the leading edge extension of this airplane, right? And when the airplane is at high angle of attack, as this vortex enters a very high adverse pressure gradient, like as the pressure increases very rapidly over this region, the vortex breaks down into a bunch of chaotic vortices. The breakdown of this vortex is really like a concentrated spatial effect, right? It's not homogeneous in any direction. So as a result, if you look at the system, you are not going to get any higher dimension if you increase, for example, the spatial extent of the system. Right, so this is the kind of a chaos we are going to be discussing first. It's really the type of chaotic systems that has a well-defined series of Lyapunov exponents that can be well characterized by actually ordinary differential equations, right? Rather than you have to, for example, in a turbulent flow, right? You really need to describe using a partial differential equation, and for example, the Lyapunov exponents, the dimension of the system would really depend on how big of a domain you are going to be choosing. If you choose a bigger domain, you have more dimensions, you have more unstable modes, and things like that. So for here, we are going to start with systems where we don't really have to think about the spatial extent of the system. That is a system that can be really treated, really completely characterized using ordinary differential equations. Okay, so of course the most prominent example of such a system is the Lorentz equation, right? So this is the Lorentz equation is actually something we are going to be spending a lot of time on when we are dealing with simple chaos, and we are going to see that the Lorentz system is almost the easiest extension from something we already looked at, like the van der Pol oscillator, because the van der Pol oscillator, as we have seen, has one negative exponent, has one zero exponent. The Lorentz equation just adds one positive exponent on top of this, right? So instead of 1, 0, 1 negative, it has 1 positive, 1, 0, and 1 negative. So we'll start with that and then look at more complex systems. And we're going to see even for the Lorentz equation, it is not extremely easy task to understand the positive Lyapunov exponent part of the system, right? We already know actually how to deal with the 0 and negative exponent when we are looking at the Van der Pol oscillator. But for the positive part, we have to actually use a even simpler system to understand its behavior. So this simpler system, again, is achieved by looking at the Poincare section of the Lorentz equation. It turns out if you connect the two centers, so these two centers are actually two unstable fixed points of the Lorentz equation. If you connect them, right, so by connecting them, I mean actually slice it through the z-axis. You're going to see that all the trajectories actually intersects the xy plane on almost a one-dimensional line. So all the trajectories, right? So if you every time a trajectory intersects this Poincare section, you record a point on the two-dimensional plane. You're going to see these the collection of all the intersections pretty much on the one-dimensional manifold. And by pretty much, I mean not exactly. Actually, it's a manifold with a slightly higher than one dimension. And we are going to be talking about what do I mean by slightly higher than one dimension, right? The dimensionality of fractal objects. But if you actually approximate, which actually to pretty high accuracy, this 1.0 something dimensional object with a one-dimensional curve, then you can really simplify that aspects of the Lorentz equation into what's known as the Lorentz map. Okay, so so the Lorentz map is really a map between a coordinate on this one-dimensional curve again to that one-dimensional curve, looking at what is the next time the trajectory comes back to that one-dimensional curve. And you can make a map that looks like that, right? And we are going to see we'll be able to understand the many aspects of the Lorentz equation, for example, periodic orbits, by looking at the periodic orbits of that map. And finally, you can retain a lot of the features of this map, which is computed numerically by this very simple map, just a rise up and down, right? We call the tent map. So this actually gives us a lot of analytical capabilities to analyze what's the behavior of that positive Lyapunov exponents. And there are several variations of this tent map. One map is that instead of a rise and fall, you can have a rise over here and then another rise over here. That gives us the sawtooth map. And the sawtooth map also gives us like the Baker's map, etc. that we'll start to look at basically during the next few weeks. All right. So basically the next few weeks we'll start with very, very simple maps that helps us understand what is going on when we have a positive Lyapunov exponent, right? And then apply what we learned to things like Lorentz equation by combining the positive Lyapunov exponent with the 0 and negative ones, right? And then we can start to look at more complex systems. So see you next week, and excited to start the chaotic part of the class.